Back in 1935, Albert Einstein cooked up this thought experiment that seemed to prove quantum mechanics was breaking the most sacred rule in all of physics, that nothing can go faster than the speed of light. At the time, pretty much everyone thought he was wrong. But decades later, when scientists finally ran the experiment for real, the results were, well, they were absolutely shocking.
Okay, so to really get what was bothering Einstein so much, we first have to talk about a fundamental rule of our universe, the cosmic speed limit. And this isn't just about how fast a spaceship can go. It's about the very fabric of reality. It's about why a cause always has to come before its effect. So, the big question, is anything faster than light? For a very long time, the answer was a simple, hard no, because any influence that travels faster than light would shatter that cause before effect rule. In fact, Einstein himself had to completely rewrite our understanding of gravity for this exact reason, because the old theory allowed for all sorts of paradoxical, instantaneous weirdness. Just take a look at this. Newton thought gravity was instantaneous, so if the sun just poof, vanished, we'd feel its gravity disappear at that exact same moment. But Einstein realized, wait a minute, that creates a paradox. The effect, Earth flying off into space, could happen before you could even see its cause, the sun disappearing. So his theory of general relativity fixed it. Gravity became a local force, sending ripples through spacetime at the speed of light. Meaning if the sun vanished, we'd still be orbiting a ghost for a full 8 minutes.
And this all boils down to one absolutely crucial concept, the principle of locality. It basically says that things can only be influenced by their immediate surroundings. This is what makes sure we all agree on the order of events. Cause comes before effect. It's why the speed of light isn't just a speed limit, it's really the speed of causality itself.
So you'd think after Einstein fixed gravity, everything was good, right? All of physics now obeyed this fundamental rule. But then, as he started digging into the very strange new theory of quantum mechanics, he found a huge problem. Something he believed violated his most important principle.
And this wasn't just some quick disagreement. This debate was epic. It spanned decades. It really kicked off at the legendary Solvay conference back in 1927, where Einstein first voiced his worries. Then it got serious with his famous paper in 1935. And finally, decades after that, a physicist named John Bell figured out how to turn this whole philosophical fight into a real experiment you could actually do. So back at Solvay, Einstein stood up and pointed out a massive issue. See, quantum mechanics says an electron isn't in any one place until you look for it. It's more like a wave of possibilities spread out all over. But, and this is the crazy part, the moment your detector finds it right here, that entire wave of possibility has to vanish everywhere else, instantly. How could the other side of the universe possibly know to disappear faster than light could get there? For Einstein, this was a deal breaker, a clear violation of locality. He famously called it spooky action at a distance. It just seemed obvious to him that quantum mechanics was relying on some kind of faster-than-light connection to make its own math work. But Niels Bohr, who was kind of the leader of this quantum revolution, he saw things very differently. His view, the Copenhagen interpretation, basically said that it's pointless to even ask what the electron is doing when you aren't looking. He argued the job of physics isn't to describe reality, it's just to predict what our experiments will measure. And on that front, quantum mechanics worked perfectly. Einstein, as you can probably guess, was not convinced. So in 1935, he teamed up with his colleagues Podolsky and Rosen, and they crafted a new thought experiment. This one was so powerful, it would put that spooky action right in the spotlight. Their paper described what we now call entanglement. Imagine creating two particles that are linked. Their properties are connected, so if one has a spin that's up, the other absolutely must have a spin that's down. Now, send them to opposite ends of the galaxy. The moment you measure the first particle and see that it's up, you know instantly that the other one is down. But how? How does particle B know what just happened to particle A? This brilliant setup forced everyone to choose a side. On one hand, you had Bohr's quantum view, which needed some kind of non-local, faster-than-light collapse. On the other hand, you had Einstein's much more sensible, local idea. The information was there all along. He said the particles were like a pair of gloves, separated at birth. If you open your box and find a left glove, you don't need spooky action to know the other one is a right. He called this idea local hidden variables. For nearly 30 years, that's where things stood. It was a philosophical stalemate. Both ideas predicted the exact same outcome in the experiment. It seemed like we could never know who was right. Until, that is, the physicist John Bell came along with a truly brilliant insight. Bell's genius was to add a simple twist. He said, okay, what if the two scientists, at the very last second, randomly choose to measure the spin along one of three different directions, like a three-sided coin flip? He realized that if Einstein was right and the particle's properties were set from the start like a glove, you'd get a certain pattern of results. But if Bohr was right and there was a spooky connection, you'd get a completely different pattern. All of a sudden, these two theories made different, testable predictions. And here's where it all comes together. When you run the numbers, the two theories actually predict different outcomes. The question is, when the scientists choose different measurement directions, how often will their results disagree? Quantum mechanics, with its spooky connection, predicts they'll disagree exactly 25% of the time. But Bell proved that any theory based on Einstein's sensible local reality has to have a disagreement rate of at least 33.3%. The debate was no longer about philosophy, it was about a number. The only thing left to do was run the experiment. And starting in the 1980s, physicists like Alain Aspect did exactly that, with better and better tests over the years. And the result? It has been overwhelmingly, shockingly clear. Every single time, the measured disagreement rate comes in at 25%. A perfect match for quantum mechanics. So the verdict was in. Nature sided with Bohr, not Einstein. The idea of local hidden variables, that sensible glove-in-a-box reality, was wrong. Bell's theorem proved that any theory that correctly describes our universe has to be non-local. Reality, it turns out, is fundamentally spooky. So wait, does this mean we can build a faster-than-light telephone? Well, the answer is no, and the reason is subtle, but it's beautiful. Even though the influence is instant, you can't control the outcome. When you measure your particle, you get up or down completely at random. Your friend on the other side of the galaxy sees their particle instantly slip to the opposite, but to them, it also just looks like a random result. You can't encode a message in pure randomness. So this prevents any wild time travel paradoxes, but it doesn't change the fact that our universe has these spooky, faster-than-light connections baked right into its fabric. So it seems like Einstein was wrong, and we just have to accept that we live in a spooky, non-local universe. Case closed. Right? Well, maybe not. Bell's entire proof relies on one basic assumption, that when you make a measurement, there's only one outcome. But what if? What if that assumption is wrong? And this takes us to an even wilder idea, the many worlds interpretation. It says the wave function never actually collapses. Instead, every time you make a quantum measurement, the universe itself splits. In one universe, you measure spin up. In another, brand new parallel universe, you measure spin down. Both outcomes happen, and you split right along with them. It is a totally bizarre, mind-bending idea. I know, but it has one huge thing going for it. It saves locality. If both outcomes just happen in different universes, there's no need for a faster-than-light signal to pick one over the other. Bell's proof no longer applies. So we're left with this profound, almost impossible choice. Do we live in a single, spooky, non-local universe? Or do we live in an infinite number of local, parallel ones? Einstein's dream of a common-sense local reality might just be true, but at a cost I don't think he ever could have imagined.